Yes, welcome back to Easy Gates K22 ECE Solutions, and hope you are able to understand and appreciate the content delivered by Easy Gate. We are trying to make the problems very closer to what is given actually in the paper. So the numbers also almost matching, and we are trying to give highly accurate results for the problems. Okay, so it's all depends on how you perceive the problem. Okay, so the perception may change little, but we are trying to make it as closer as possible to the one happened in the paper. Okay, yes. Let me get into the next problem. The next problem is from electrical circuits. Yes, this is what given. It is looking like a two-port network. Input port V1, I1, output port V2, I2. Maybe you can also mark the potentials of V2 as plus and minus, like V1. And given the input port is excited by 10 volt. Yes, input port is excited by 10 volt. Yes, what is exactly the problem? We'll see. So in this given circuit, the resistor R, which is connected between terminals A and B, is varied. R is getting varied. So when R is varied, the connection between V2 and I2 is given graphically. Okay, so the voltage versus current characteristics at the output port is given. Simply V2I characteristics is given. Okay, what is given? It is 5 volt when the current is 0 milliamps. It is 4 volt when the current is 4 milliamps. Remember that what is given in the x-axis is minus I2, not plus I2. Okay, so that's a little play. So you need to play carefully. So that means that the current is not actually going into the output port. It is coming out of the output port. That's how we need to take it if you want to remove that negative sign. Okay, we'll see. Then what is really the problem is? So the problem is this: when R is getting varied, this is how V2 and I2 vary for the boundary. When V2 actually takes a value what? V2 is between what? 4 volt and what? 5 volts. V2 varies from, so that means we are varying R. When R is getting varied, V2 varies from 4 to 5. Okay, it is falling. Okay, so as current is increasing, the voltage is falling. That's what it says. And what about the minus I2 as per the data given? The minus I2 data. So it is, so when it is 5 volt, it is 0. So therefore I can say it is, okay, so it is 0. Yes, it is increasing. 5 volt, it is 0 milliamps. As the voltage decreases, the current increases. So current increases to 4 milliamps. This is what given. This is your V2 and this is your minus I2. That is given graphically. We have to play with this. Okay, fine. Then what is exactly the problem is? Okay, so he has given, if this is the condition, when R varies, this is how the connection between V2 and I2 exists. Means if I replace R by this equivalent, that is having a resistance of 1 kilo ohm and a battery of 10 volt. If this is connected in the place of R, then what is the current? I2. What is the current? I2 in the given circuit. Problem is, what is the current? I2. Okay, it's not talking about minus I2, it's talking about I2. What is the current? I2 in the given circuit? Yes, that's a problem. So how we can plan? So we can do one thing. I can call this as a whole circuit whose internal excitation doesn't change, because the input port is excited by a constant voltage. Let me take this as V2 and I'll take this current as I2. Okay. This is my current. So as per the, I took it positively now. Therefore, the graph is going to be this now. So this is my I2 instead of minus I2. This is going to be V2 and the 2 points. One is 5 volt, another one is 4 volt, and voltage decreases, current increases from 0 to 4 milliamps. It is in milliamps and this is in volts. Let me take. Okay, yes. This is the point. So here we have our resistor R. This is variable. Okay. So what we can do is, Yes. What we can do is we can replace the entire circuit, which is looking from A to B. I'm looking from terminal A to B as a practical source. A practical source. I'm modeling rest of the circuit as a practical source of Vs and Rs. That means it's equivalent to Thevenin's. We are applying Thevenin's for this. That means we are Theveninizing entire circuit looking from the terminals A and B. But for that, you need to disconnect your R. If you disconnect your R, there is a problem. What is the problem? If you disconnect R, then the current is always going to be zero. Then we don't know what is the circuit. Okay, so looking from the terminals A and B, we can't connect properly. Okay, it's effectively equivalent to Thevenization only. That means I'm going to model the rest of the circuit looking from the terminals A and B as a single voltage source in series with a single resistance. That means it's a practical source modeling. So let us do practical source modeling for this, and then we'll keep the R connected. We'll answer the problem. That is a plan. So let me model the entire circuit as a practical source. That means what I'm going to do, I'm going to keep the problem very simple. I'm going to have a DC source of Vs, entire circuit I'm modeling as a practical source, and a resistance Rs, simple, between the terminals A and B. And then I'm going to connect the variable resistor. So how it is going to help our problem? Because current responses are given, voltage response is also given. This is still V2 and this is still our I2. Now it's easy. We have two V2s and two I2s. That means we can form two equations, function of two unknowns, Vs and Rs. Then we can get Vs, Rs, then replace the R by the given setup. Then it's a very easy problem. That's how the problem has to be approached. Instead of a two-port network, you just go by practical source modeling. Okay, so the curve V2I curve is given. Exploit the terminal characteristics of a practical source and assume this is a practical source terminal characteristics. You can forget everything backward. Then you model entire setup as a practical source of Vs, Rs. Then you can help yourself. That's a plan. So now what is given? So current is 0 milliamps. When the current will be 0 milliamps? Only when R is equal to infinity ohms. R is equal to infinity ohms, you'll get the current. So this I2 in the marked direction. That's very important. This is I2 and this is V2. So what is I2 now? It is equal to 0 milliamps. I2 equal to 0 milliamps. What is V2? It is 5 volt. That means this is a given setup. Let me have a copy of the same. Yes, now let me play. I2 is given 0 milliamps. Okay, and V2 is given how much? 5 volts. V2 is given 0 milliamps means no current. So that means R must be infinity. So this is equal to 5 volt and here there is no current, 0 milliamp. Therefore, there is no loss across RS. Therefore, assuming this is the reference 0, this will be 5 volt and no gain or loss of voltage. So this is also going to be 5. Therefore, Vs is equal to 5. So the first condition straight away gives Vs equal to 5. Okay, so now let me take this Vs equal to 5 for the next condition. We know the open circuit voltage. Now the next condition is voltage is 4 volt when the current is equal to what? 4 milliamps. Now let me force a current of 4 milliamps. Okay, and what is the voltage across this resistor? It is given as 4 volt. If that is the case, you know by Ohm's law, your R must be equal to. You don't need R actually. You need only Rs. Okay, we'll go for Rs straight away. So let me take this as a reference point. If that is the case, this potential will be 5 volt and this potential will be equal to 4 volt. That means the drop across Rs is only how much? 1 volt. And you know very well the current through the Rs that is equal to 4 milliamps. Therefore, straight away, you know your Rs. What is Rs then? 1 volt divided by 4 milliamps. 1 volt by 4 milliamp. That's a very interesting problem. 1 by 4, it's going to be 1000 by 4 ohms, nothing but 250 ohms. Yes, you have modeled entire circuit as a practical source of Vs and Rs. So you got Vs equal to 5 volt. The moment you see the current 0, open circuit voltage it is. So you can straight away take 5 volt as your open circuit voltage Vs. And you have to play carefully for Rs. For that, your data is given So you play for RS. Now you know the entire circuit modeled as a practical source of VSRS. You can happily connect whatever is given. So what is given between A and B? So I have modeled this as a voltage source of Vs of 5 volts. And here the equivalent resistance, the practical source equivalent resistance Rs, that is equal to 250 ohms. This is still your point A, still your point B. Now you're going to replace A and B by what is given. What is given? So you have a resistor of 1 kilo ohm, you have a battery of 10 volt. That's all. So this is how you need to help yourself in the examination. In the examination, no one will help you, only you have to help yourself. Okay? Yes. Yes, take this point as a reference, 0. Then this point potential will be 5 straight away. And this point potential will be what? 10. And therefore, the net difference is going to be, this is higher potential and this is lower potential. The net difference is 10 minus 5 is going to be 5 volt. Current is actually in this direction. Current is actually in this direction. Okay, yes, this direction only the current is given in the actual problem. See that. The current is given in the actual problem only in this direction. Yes, in this direction only it is given. So what's the current I2 means? Therefore, the actual current is existing in the given direction. So your answer should be positive. Yes, what is that current? Okay, yes, what is that current? So 5 volt divided by, so the current is equal to 5 volts divided by the net resistance, that is 1250, 1.25 kilo ohms we can say. So it is nothing but 4 volt per kilo ohm. So 1 kilo, that is nothing but 4 milliamps. So the perfect answer for this problem is 4 milliamps. Yes, interesting. Okay, instead of taking the problem by two-port network way, that's a way to approach this problem. You model entire circuit as a practical source, then make a simple series circuit for the given data, then a simple circuit analysis will give you the answer. Okay, yes, and hope you enjoyed this content and keep sharing and also subscribe our channel. Okay, we'll update you with one more problem soon. Thank you.